Hi there, this is P0werTech and we are presenting our Smart Trip DC breaker. Entering our problem space, the emergency event database defines a disaster as an event that overwhelms local capacity, necessitating external assistance. Now there has been an increase about 492% in the number of disasters over the past 50 years, and last year we see 46 million people were approximately displaced by disasters. Now in response to this, relief camps are mobilized to these affected areas. And these camps provide basic living needs for victims, such as fresh water, food, medical supplies, and other equipment that is needed. And some of these camps are DC powered, whether it is through panels or batteries. And these camps need reliable protection to really provide this assistance to these victims.
Our solution is the DC solid-state circuit breaker. This is how we safely protect DC-powered relief camps, and the types of protections that we protect against is overcurrent, undervoltage, and ground faults.
On the left, we have our PCB, which includes two boards on it. The high voltage board handles the conduction, and it senses parameters that help our control board on the right make decisions on when to trip the circuit. It uses a lithium-ion battery and an FPGA, which makes calculations faster than a typical microcontroller. And on the right is all our components in the final enclosure.
And we need to use an inverse time curve as it has a built-in delay, letting momentary surges pass without triggering a trip. On the y-axis, you have the time in seconds that it will take the trip based on the current of the x-axis, where increasing current results in lower time taking the trip.
The schematic made in Plex software models the main conduction of the breaker and the short circuit fault to simulate a trip. We use this model to calculate the energy capacities for the MOVs. So the larger the line inductance and the larger the peak current, the greater energy is discharged into the MOVs. This is a functional demonstration of our circuit breaker. The inverse time behavior is captured on the right.
For the thermal model, we compared various heat dissipation methods, having an internal versus external heat sink. An analysis was done at steady state with maximum energy dissipation, and we found that the external heat sink was approximately 30 degrees cooler at the highest temperature. And on this graph, the y-axis is the temperature, and the x-axis, the thermal node, indicates different points on the thermal resistance model.
Our product features an aluminum enclosure engineered for strength while keeping weight relatively low. Components include a user interface with a set reset button and LEDs to indicate whether it is on or off. Cable glands are used to keep wires secure and watertight. A humidity indicator is also being used to keep track of relative humidity, and a silica gel packet will be used to keep the enclosure from getting too moist. Components are sealed with precision-fit gaskets, ensuring full IP67 protection against dust and water intrusion. And with a high-performance external heatsink, heat is efficiently dissipated, allowing the system to operate reliably and safely under demanding conditions.
We created an intricate enclosure meeting the IP67 standard while also withstanding the specific thermal requirements of each component. And to enhance the texture speed, we used an FPGA as our microcontroller. This is our solution. Thank you.
To have a more in-depth view of the inverse time curve behavior and how our breaker works, here we have a video showing the time to trip at different rated currents. As you can see, the LED is turned on, and once the current exceeds a certain threshold in the inverse time curve, the LED turns off. And this is because the inverse time curve is coded into our FPGA. Also, the speed in which the breaker trips depends how severe the current is, as a higher rated current will make the breaker trip faster. The next clip will show how our enclosure is dust tight and protected against water immersion to meet the IP67 requirement. Hey everyone, P0werTech here. To show that our enclosure is waterproof, we have cotton candy here. As everyone knows, cotton candy dissolves in water, so if it doesn't dissolve, it's waterproof. Our enclosure was successfully waterproof, and if you would like to learn more about our project, please visit our booth at the Capstone Expo.